my talk. I'm a little bit nervous now because I think this is my first time to attend the Neuromorphic workshop. And I'm the PhD student from Dr. Hassler and Dr. Minch. So actually I learned 14-gate stuff and also circuit design from these two professors. And right now I'm at National Taiwan University of Science and Technology, which is in the Taipei city, and then just close to the NTU, National Taiwan University. So, and in our school, we have about like 10,000 students, and half of them are graduate students, and we also have about like 1,000 of international students. So, if you have chance, like we are welcome to Taiwan. And my lab is called Intelligent Sensory Microsystem with advanced reconfigurable technology. So we try to build circuit for AIoT, and then because we are in Taiwan, so actually we got very cheap tape-out resources. So we actually have a lot of chip design and fabrication and major facility. So we actually design like energy harvesting, analog front end, and then ADC, and then computing memory, and also some 14-gate programming infrastructure. And then my research interest actually is the low power and low data bandwidth, low latency circuit for biomedical and AIoT applications. And this kind of application, the signal usually exists sparsity. So I try to design circuit take advantage of this sparsity. And also because of the 14-gate, the wonderful device you just heard from Dr. Hassler. So I think we try to use that to expand the design paradigm, and then so that we can try to get a low power analog circuit, low noise, and high linearity. So I'll try to talk about that in this today's talk. Because I heard a lot of students actually talk about noise and also linearity and also bandwidth. I think in terms of a circuit, we can try to use 14-gate technology to actually design superior analog circuit based on this technology. So right now we are actually still designing like analog embedded flash technology for low power sensory circuit, and then energy harvesting, cognitive computation, and also we have also involved some efficient power management circuit like bulk converter, this type of thing. And so this is the energy harvesting circuit we developed. So it's like for TEG or solar cell, we can have like 3 input with the MPPT circuit, and then also have the energy reuse. And then we have the whole front end chain, and we are going to talk about low noise amplifier, filter, buffer amplifier, and ADC today. And we also have a computing SRAM. And then we actually also design an analog gated recurrent unit with a professor at the Dartmouth, Cofield Dame. So the story actually starts from like Cornell and Georgia Tech. Like we try to use a 14-gate to have a fast prototyping. So if you have the APA, you can see like if you design analog circuit, usually you take about like 6 months to get your first design run completely. And then if you can use the programmable platform, actually you can try to synthesize different algorithms within like 3 to 5 minutes. So actually this is the original motivation when we try to devote into the 14-gate technology. And 14-gate is just what just mentioned. Actually, it tries to store the charge on the 14-gate, and because the charge actually is surrounded by high quality oxide, so it will not leak out. And then if you use the charge retention rule, actually you can see this 14-gate voltage actually is the weighted voltage sum with a charge term. So in this kind of structure, actually, you can perform voltage summation easily without any power consumption. And you also have the ability to tune the charge with hot carrier injection and tunneling. So in Georgia Tech, actually, we can program the charge precisely so that the current precision can be within 0.2%. So this is like 128 different 14-gate devices with different target current, and this is the error. And then because you have the precise programming precision, so you can actually do lots of interesting things. I think Dr. Hassler just mentioned about capacitive circuit, so I want to emphasize this because usually people use KCL to design circuit, even so like Cadence also use the KCL, but actually it's kind of limited So if you think about this charge conservation law, actually KCL doesn't solve this initial condition if you don't give the correct initial condition of the charge. So if you have the control of the charge, actually you can use capacitive circuit to perform weighted summation without any power consumption and also without noise. If you use the resistive circuit, then you have the 4 KTR noise. But if you use the capacitive circuit, then you don't suffer from the noise. And then also the DC level can be tuned. And then the output voltage is a weighted sum of the input voltage. If you don't do that, you can imagine you have to use the amplifier. You have to use the amplifier and then power consumption and then also the current need to go through the resistor to do the summation, KCL, right? So they are all costs of the analog circuit. And then so this is kind of the fundamental benefit if you can kind of precisely control the charge. So based on that, we actually try to have like complete front-end chain, and then we try to look into individual circuit carefully and to see like what can we do to have a better advantage of conventional analog circuit. And then we also design a cognitive computation circuit, and so that we can try to bypass this conventional scheme of the data conversion. We want to perform like analog to information directly. And then we also try to do energy harvesting so that the system can be energy autonomous, right? And then we also look into high efficient switching converter, like buck converter, what is the most efficient way to convert the energy to the system. So this is kind of the scope of the lab right now. And today I'm going to focus on this blue part.
So question,
yes.
For the previous slide, not this one, the one before. So that's not entirely true that there is no noise. It's only because you're driving the voltages through some source resistance.
If you calculate noise, actually all the inputs should be grounded. So because the original of noise actually is the time arrival difference between carriers. So if you have capacitor, there's no DC current, so there's no flowing carrier, so there's no noise source.
Yeah, but only if you're using it as a static system. But if V1 and V2 are changing.
Yeah, but yes, if you connect this to transistors, then this transistor will give you noise. But I'm just trying to say this structure itself will not introduce extra noise. The noise will come from outside. Yep. So compared with resistor, actually resistor itself will give you like 4 KTR noise or 4 KTG noise. So this is a neuromorphic workshop. So I'm thinking about neuromorphic engineering actually from the circuit point of view. So what to me neuromorphic engineering means like supposedly should have some hardware reconfigurability because like the brain structure and also the neuron structure are all the same, right? But different neuron, different part of the brain actually can perform different functionality. So that means like reconfigurability actually is the essential principle for neuromorphic. And also nonlinear operation, right? Because none of the components in the neuron or in the brain are linear. And also asynchronous timing, parallel and scalable architecture, and distributed memory. And then also this is the system fusion of sensing and computation, and analog digital, and also hardware and algorithms. So I think this is kind of my point of view of neuromorphic. So I try to apply this neuromorphic engineering principle into analog circuit design level. So to me, I'm very nervous today because I listened to all the experts from the world and then talking about the system level and spectrum network. And for me, I'm just an analog designer. And I think in my school, most of the students are master students, so their dream is to become an analog circuit designer. So they hardly think about algorithm because it seems like too complicated for them. So I try to apply this kind of neuromorphic engineering principle down to the very, very bottom level. So I think the major difference for me is like in my school, I have kind of infinite availability of chip design, so I can ask the student to tape out chips without costing anything. And then, so that's the reason why I think it's kind of cool, right? So we just use these kind of resources to see like how neuromorphic engineering can improve the analog circuit design philosophy. So I'm going to talk about this circuit if I have time. And then I think each of the circuits actually emphasize on noise, linearity, power consumption, bandwidth, and then those kind of fundamental analog circuit designer will care about. So maybe you can take a look at how neuromorphic engineering can improve this kind of design spec. So for noise amplifier, we know like you use NEF to kind of quantize the trade-off between noise, current, and also the bandwidth. So before Reed Harrison have the cat feedback amplifier, actually all the NEF is above 100. And then because of the cat feedback structure is proposed, right? And then now the NEF can be down to below 10 when Reed Harrison proposed this structure in 2003. So at that time, he doesn't try to use a 14-gate technology, so he proposed this pseudo resistor so that this nonlinear device actually can adjust the charge at this 14 node automatically. So this is this pseudo resistor actually is a back-to-back connected BJT diode. So it is nonlinear, so the equivalent impedance can go up to 10 to 12 ohm. And with this kind of resistor, actually you create a low-pass corner, right, where it can be below 1 hertz. And then for high-pass corner, actually we can use the GM or the current of the OTA to tune the bandwidth. And then lots of people try to design low noise amplifier OTA itself. So in our lab, we also try to do the same thing. We just try to use complementary differential pair and then they know it with each other. So all the noise component come from this 4 transistor, but this 4 transistor also contribute to noise, to GM, sorry. And then there's no significant component actually contribute to noise without contribute to GM, so that the equivalent NEF can be down to 1 watt kappa, which is 1.47. So this is the first AONA with the NEF below 2 with a measurement at that time. And then, so this is the first chip I made in Taiwan. And then I do the layout by myself, and I have kind of rusted, so it's kind of ugly. And then when we try to do the ECG measurement, actually we found lots of distortion in the low frequency side. And then we just figure out like, oh, the low frequency corner, the signal goes through the resistor, and the resistor itself is nonlinear. So apparently this gives us a distortion. So we try to find a way to solve it. So we look into different kind of pseudo resistor, and we can see this gate balance pseudo resistor actually can perform the best, because if you look into the large signal behavioral transistor, if the gate of the transistor can be the mean value of the source and drain, actually you can achieve a very linear IV characteristics. And of course, if you can also do the same thing for the bulk, they'll even be better. But I think for us, we just try to have a symmetric structure for the bulk connection. And for the gate, we use a 14 gate to have the natural voltage sum without any power consumption. And then we can improve the THD with more than 20 dB without increasing any DC power at all. So this is kind of the simulated resistance valuation with different kinds of structure. So with this kind of gate balance pseudo resistor, actually you can see that now the input and output of the ECG signal will not have any discrepancy at all, not from our eyes. And then this is the layout done by my PhD student. So the same area, it can contain like 4 of them. So student is good. I need good students. And so with this improved version, actually the NEF can be 1.88, and also you can see it with the within 0.1 THD, which means like 10 bit resolution. This dynamic range can be also be up to 62.8 dB. So which means like this AONA fully support 10-bit resolution, no matter in terms of noise or linearity. And the power is also awesome.
So what do you do with the reverse bias diode in the pseudo?
Oh, I just try to make the diode connected and then have a symmetrical structure, so that still like kind of symmetric. I think it creates some nonlinearity in these two ends, but it's kind of sufficient for this application. And then that's why we use 2 of them, so that when the voltage drop is smaller, actually linearity will be better. If you look into other pseudo resistor papers, actually they use tens of transistors to make the pseudo resistors. So this kind of answer the question of noise, right? If you try to design low noise amplifier with the 14-gate technology, you use the capacitor instead of resistor, actually you can achieve low noise, high linearity, and low power consumption. I think this is the first take-home message I hope I can convey. And the second circuit is the filter, and then for filter, actually, you know, like the input amplitude has been amplified, so you don't care about the noise that much, but you care about linearity, right? And then also for filter, lots of different applications need to have different like filter parameter, like the quality factor, gain, bandwidth, and also some people want to have a low pass response, some people want to have a low pass or band pass response. So we choose this 4 OTA C structure, and then this structure actually can give you the low pass out, band pass out, and when you try to tune the current, actually you can have different bandwidth, different gain, and different quality factor. So we think this is a nice structure to do like programmable, reconfigurable filter. And the only problem is like the linearity. Linearity is because of the, in biomedical application, the current is so low, so differential pairs is operating in the subthreshold region. And so the input linear range, if you look into the GM less than 1% variation, this input range is only like 14 millivolt, which means like the amplified input signal will give you lots of distortion. So we look into lots of different topology that can increase the linearity. And then we are thinking about like how do we evaluate which structure actually is better. And then so we propose a linearity efficiency factor just like the NEF. And then try to trade off the power consumption, input linear range, and GM. Because and this linearity efficiency factor is actually pretty interesting because previously when people talk about if you want to increase the input linear range, actually you can always use the capacitive input attenuation to achieve like infinite input linear range if your attenuation is almost 1 to almost 0, right? If you have a gain of like 1/1000, actually increase the input linear range by 1,000 times. But the cost actually will be the power and GM, and so these two, right? So if you use this kind of LEF factor, actually the input attenuation, and then also if you operate your transistor in the subthreshold region, the input linear range is not fixed, it's not moving, but the current and GM is proportional. So this LEF will not change if you operate your differential pair in subthreshold region at all. So that means like this LEF doesn't change with your operating point. And if you try to bias your transistor in above threshold region, then input linear range is proportional to square root of the current. And also the GN is also proportional to square root of current. And then if you have this equation, the LEF is still not changing. So this means like this is a very nice FOM to indicate which topology to do linearization will be more power efficient. So the lower the LEF, the better, right? Low power, large linear range, and then large bandwidth. So we look into these different topology, we found like all these DDDP actually achieve a lowest LEF. So we look into it and then we just try to extend it. So instead of just have two diffusers, two differential pair, we try to add more diffusers and we try to add more differential pair and then sum them up. So this is kind of like you try to solve the linearity problem with nonlinear combination. So this is called a nonlinear cancellation. So use lots of nonlinear differential pairs, sum them up, and the overall GM will be very linear. And then if you do that, actually the LEF can be down to 0.15, which means like you can just use 15% of the power to achieve the same linearity if you use the capacitive input attenuation. So this is a huge save. And then if you use the complementary differential pair again, actually this LEF can down to 0.7%, which means you just use 7% of the power to achieve the same linearity. So, so this is something we do, and then also, of course you add more component, you add more noise sources, and then you can calculate the noise sources and then try to get the input referred noise. Actually, noise penalty is only like 19%. You increase 19% of the noise, and then the power increased by 15%, but your dynamic range increased like 14 times. So that means like you actually get a huge advantage in the dynamic range. And then this is the chip we fabricate. We fabricate 6 biquad, and then these are all in 14-gate device. And then we have the 14-gate programming structure. And then we can measure the OTA, so you can see it's kind of flat. And of course, like this flatness depends on the component mismatch. So we use this, just like the FinFET, we use the same unit element to do the transistor in parallel and serial. And then we also actually we try to write the particle optimization algorithm to calculate what is the right number of the transistors to be in parallel and series, so that all these transistors are in array with the, like the dummy devices. So try to make sure they are matched. And then we can program it. So we can program to have a 12-order Butterworth filter response or 6-order trip shift bandpass response. We can also program to have a 6-order low-pass basal response with a constant group delay. And then that means like with this kind of technology, when you try to change the filter response parameter, you can just like do it within like maybe 3 to 5 minutes instead of like have to redesign the whole analog circuit or try to find a component to trim. And then based on that, we are thinking about the nonlinearity of the circuit. So we say like, oh, we can use the nonlinearity of the circuit, try to design LDO. So for LDO, actually, we use the 14 gate so that we can use the MOS transistor as the pace transistor so that you can have a very nice line regulation, right? Compared with PMOS transistor, and also you don't suffer from the dropout voltage. You can still have a low dropout. And then we use the transistor to capacitor to do voltage sensing so that the feedback ratio can be 1 instead of the resistive divider. And then we use the charge stored on the capacitor so that this voltage can be the voltage reference. Then we don't have to use the band gap reference at all. And then we can use this output voltage to fit into the error amplifier directly. So we have very nice low regulation. And then also we don't need extra star circuit. So we fabricate the chip, and then we also try to improve the traction with the low quiescent current. So instead of using the differential pair type of the differential type of input stage, we use the class AB type of input stage, so that if there's a discrepancy or change at the load, then the error amplifier actually suffer from large voltage difference, and then you can actually use a lot of current to charge this input control gate. And once everything is settled, when everything is in equilibrium, and the current will get back to the low quiescent current level. So that means like you can achieve the fast transition and the low quiescent at the same time. So we fabricate a chip, we can program the output voltage with different kind of voltage level you want, and also we don't have to do any special thing about start. And we also measure the temperature response. Actually, we got 22 ppm per degree C, which is the temperature coefficient of the PIP cap. And then we think of the nonlinearity to design ADC. Usually, like if you have an ECG signal or biomedical signal, lots of signal actually concentrate on the low voltage region or low amplitude region. So if you try to use conventional ADC, actually this large amplitude will give, you have to try to, you have to flip or switching the MSB cap, but the MSB cap switching actually consumes most of the power. So if you know your amplitude already, you actually can bypass switching those big capacitors to save power. So we said, oh, if you try to make your bypass window size as a 32 LSB, you can see most of the signal of the ECG actually concentrate in this window, then we can actually achieve lots of power saving. So conventionally, people use a comparator to set a threshold window, and this threshold voltage need to be very accurate, and then the comparator also consumes extra power. So we propose this dynamic proximity comparator using current correlator. And so if you have a bump circuit and then you have this bump of current characteristic, and then you compare with differential pair characteristic, and you can actually see the intersection, and this intersection actually gives you the window size. So you use that, and then with a two-stage comparator, so the second stage will give you indication whether the input signal is inside the window or outside the window. So we propose this dynamic proximity comparator. So in the first beginning, the polarity latch actually compare this pseudo differential pair, and then later on, this bump circuit actually is activated, and the second latch actually give you the proximity decision. So by doing so, actually, with 32 bypass window, we can actually save 39% of the power if you have an ECG signal. And if the ECG signal is less than full scale, actually the amount of saving can be even more. And then this kind of nonlinearity actually also gives us very good inspiration to design a buffer amplifier. So most of the buffer amplifier actually is limited by the slew rate, right? And if you look into the biomedical signal, lots of the signal only have a very short period of time, have a high slew rate. For conventional analog circuit design, you use this worst scenario to design your tail current, and then no matter what kind of signal input into your circuit, actually you keep consuming huge amount of current, no matter what is the portion of the high slew rate region. So we look at that, we say like, oh, 94% of ECG or like 96% of the spike, actually their slew rate requirement actually is low. So we say like, if people try to use the sensing circuit and then try to control the tail current, but in this case actually it will be slow, right? Because once you finish the loop, actually the signal has already passed away. So, and then people talk about like class AB differential pair, super class AB buffer amplifier, so that you don't have to be limited by this saturation current, hypertangent type of saturation current, and you try to use the hypersine transfer function. But this type of circuit actually also suffer from linearity, because this circuit actually have limited input linear range. So I think that Professor Minch, his circuit is nice, very rail to rail, and then also for in-gate you can have local feedback, and then you can have a very nice power efficiency. So we choose his class AB input stage, and then we just merge with the cap feedback structure. And then this cap feedback structure actually will give you information of the output voltage and the input voltage, right? Input capacitance sends the input voltage, and the feedback capacitance sends the output depending on whether this input and output will change or not, this this floating gate circuit, or the supposedly should be virtually shorted node, will be changed, right? If everything is in equilibrium because of high gain feedback, these two will be shorted. Once these two are shorted, then this circuit can have a low power. And once there's a change, and then these two voltage will be different, then you can actually create lots of dynamic current and then to increase the slew rate. So we made the circuit, and then this is class AB input stage, class AB output stage with the Minch cascode biasing. And then when the input have a sudden change, then this input amplifier actually have a voltage change, and then you use a large current to make the output to be balanced as soon as possible. And then once output is settled, then this current back to the low current level status because of the short virtual short between the 14 gate, right? And then everything will be back to low quiescent level. So by doing so, we actually can create an amplifier with autonomous supply current adaptation based on input frequency amplitude, which means like if you input a low frequency signal, then the power will be low. Only when the frequency is high, then this amplifier automatically increases its power consumption, right? And also, if you look into the, so this is amplitude response, this is a supply current, right? And then if your input amplitude, sine wave input amplitude is small, then this amplifier also consumes low current. If the amplitude is large, then the amplifier itself increase the current consumption automatically. So that means like this amplifier kind of get the intelligence, right? Instead of like just have fixed spec of the bandwidth and the power consumption. Depending on your input signal, it change automatically. And also if you try to look into the bandwidth, also the same thing. The bandwidth also depends on the input amplitude. If the input amplitude is small, then the bandwidth is, you don't need to change dramatically, so the current is small, then your bandwidth is low. If the input amplitude is large, then your bandwidth can be increased automatically by using this circuit. And if you look into the step response, also the same thing. this peak current only occurred during the age. So without, out of the age, the current get back to the almost low quiescent current level. And this peak current also depends on input amplitudes, which means like when the input amplitude is small, then the circuit sense like, oh, I don't need that much current, so I just give you a small current, and then you have enough slew rate. So the slew rate also depends on input amplitude. So to me, I'm very proud of this circuit because operational amplifier actually is a very traditional, the most traditional circuit for analog society, right? And then we try to break this existing design paradigm, and then we try to have an analog circuit which can adjust the bandwidth, slew rate, and power consumption automatically based on the input signal property.
So does it introduce distortion?
No, actually the distortion is very nice because the distortion usually caused by like your current cannot supply sufficiently fast. If your current can supply sufficiently fast, then actually the distortion is very nice. Because, and also our amplifier has the structure of the amplifier actually is a high gain. It's a 40 cascade structure with the KSAB, so it's a GMRO3 times of the open loop gain, right? And then feedback, so it's a feedback using the feedback system with a feedback linear component capacitor, so linearity is very nice. We only care about like if you have sudden change, if your input amplitude is so large, right? If your circuit cannot catch up with the change, then you got the distortion. So now we have a circuit, you can sense the input change, you can sense the output change. And then the circuit itself will adjust the current consumption by itself. So that actually if you look into the linearity and then also the bandwidth and power consumption, FOM, actually our circuit actually perform the best. And then we also use the same kind of design principle into ADC input driver. So people usually seldom talk about input driver. Also, like people talk about ADC a lot, but driver power consumption actually is like usually 10 times more than ADC. So a lot of people talk about like how do we decrease the capacitor, the sampling capacitor, the delta V, and also the sampling time. And we are talking about like we can change the current of the input driver directly. So if you look into the sampling phase, actually only this initial timing is the slewing phase, only the red part. And once the slewing phase is done, actually once you are in the RC slewing phase or in the whole phase, supposedly this input driver doesn't need to consume power at all. So we try to say like, and then we can use the same kind of design philosophy. We only have the high power in this short period of time, and most of the time input driver supposedly should be quiet. So we propose a circuit, design the circuit, and then we measure it, and then also we can try to compare with the class A conventional input driver, and we can save lots of power. And then so we integrate everything into like a multi-channel front-end chip, and we also try to do like red experiments, and then just try to see if we can integrate everything together or not. And we are still in doing that too. And then beside that, we also think of like analog to digital conversion, and AI is can we do like analog to information directly. So we try to see like can we do the reconfigurable computation unit matrix. And this is kind of like because in this AI age, people try to talk about like sensor fusion. If you have ALM, you have lots of sensors, especially like robotics will be the next big thing, right? So you have lots of sensors, and how do you interact with the large language model? So conventionally, people use ADC, DNN, token, and then ALM, token, and then DNN, DAC, and then actuator. So you can see actually a bottleneck, no matter it's the bandwidth, the data bandwidth, or the amount of memory, actually is in this green line, or in these green lines. So if you can do this tokenizer and decotokenizer, you can try to do analog to token directly or token to analog directly. Then you can kind of get rid of this data transfer bottleneck. So we try to say like, with this kind of device, we can also have real-time mode adjustment. So if you can actually, based on the signal information, like how if this signal is of interest or not, try to use this RCCM to adjust the mode of this analog circuit. And then you can actually make a very low power, always on front end. And so for this, we can say the challenge actually is without ADC, everything should be done in analog, right? And then you should be diverse because you don't know what kind of application you are going to use, and then so you need to have some probability. And at that time, we decide to use SRAM, and then you also need to support different kind of data formats, and also hopefully it can be a tileable architecture or scalable architecture. And then the data movement should be avoided, so we decide to do computing SRAM, and then the process variation, and then you need to do the hardware software co-design and have some collaboration strategy. So we look into this ladder-based DAC. So this is also the structure I learned from Dr. Minch. And it is a very nice structure. It is, all the transistors are identical. And this topology are modularized, which means like I can slice it in bitwise. And also I can duplicate this LSB for tooth complement because this is 1, 1, 2, 4, 8, right? So for tooth complement, actually I have extra 1 can be used. So then I can use this ladder-based structure to have a 2-layer. This is just the illustration. And then I can have the input and the digital weight. I can do analog input with the digital bit multiplication directly. And then if this is input in digital and the output and the weight is in digital, I can also do digital multiplication directly. And because this current flows through this ladder DAC, so multiplication is done naturally, so you don't actually worry too much about the device linearity to cause distortion. You only care about the matching of these the identical size transistors, and then it's much easier. So we actually try to build to merge this ladder structure with the 60 SRAM and this layout. And then we can have this input PE and weight PE, and then we can tile them into an array. So we tile the array, and then we can try to build some analog activation function. So we support radio, RBF, and hypertension. And then we can have the current receiving block and then the current transmitting block so that everything can be tiled up. And so this is the measurement result. We can actually perform 1 quadrant, 2 quadrant, and 4 quadrant kind of multiplication with very nice linearity. And the most cool thing is like you can actually input 4 different or actually 16 different analog time varying waveform and then perform multiplication accumulation in real time directly in the analog domain. So that means that you actually can perform real time without memory, without clocking. You can do immediately information transformation or cognitive computation. So this is the activation function we get, and we can also see we can tune it. And right now we tune it with SRAM, so we can use the SRAM to provide different kind of slope. And then we try to use 4 different chips to recognize MNIST data sets. And because right now the resolution is the input is limited, so we try to do average pooling, and so the image is a little bit blurred. And then we try to use 4 different chips, 3 layers, and then we can perform like MNIST up to like 91.2% of accuracy. And most of the degradation is still like somewhat mismatched in the transmitter and receiver side has not been fully calibrated. And then we also try to do real-time get a recurrent unit. And then with this, we try to have array of we use the RCCM, the SRAM-based device to store the weight and then the current, and then get to the low-pass filter, and then have a feedback loop. And then we can use that to have a 4 hidden variable kind of structure. And then this is like we try to use neural spikes to do spike sorting. And we try to use PyTorch, which is the digital simulator, and then Cadence, which is the analog circuit simulator. And then look at the output of this network, and you can see the correlation is pretty high, more than 90%, which means like I can train the network in digital offline, and then once I get the weight, I can install them into the analog chip, and then supposedly I should get something similar. So this is the first version of the chip. This is the preliminary measurement result. So I can identify this is spike 1, this is spike 2, and the equivalent power efficiency is about 3.6 TOPS per watt. And this is done in 0.18 nanometer process, 0.18 micrometer process. So future opportunity, like our central actually is a reconfigurable power efficient circuit design, IC design. So we look forward to collaborate with different experts from different fields. Actually, in my personal experience, I collaborate with signal processing person, sensor person, and memory. Right now, I'm still looking for, and then like new network, and also like like third generation semiconductor. So yeah, this is kind of the. I think this is a very interesting field, like to have an IC, and then you can interface with different kind of expertise. So, yeah, sorry. This is my group. So I have right now about like 20 master students. My only PhD student is going to graduate this month. So this is kind of the composition of my team. So most of the students come here to learn about analog circuit within 2 years, and then they try to make big money. And then so I have to teach them analog. They cannot, they don't have the patience to do like too large scale stuff. So that's why I try to get like what I learned from Dr. Hustler and Dr. Minch down to the analog circuit level. And I hope my talk can kind of answer some of the student question about the 14K technology in terms of noise, linearity, bandwidth, power efficiency, this kind of stuff. And then I think this is very interesting, and I really appreciate this opportunity for me to be here, to be part of you, and then listen to so many wonderful talk. And if you have any question, you are welcome to have some discussion. I'm really happy to co-work with all of you. Thank you very much.